Hello everyone. Today I'm glad to present our work understanding Routable PCIe performance for composable infrastructures. Empowered by emerging cluster interconnects such as Routable PCIe and CXL, composable infrastructures decouple resources from their physical location and create a resource pool. Now, remote computing resources can be accessed by host servers as if they are local ones. The composable infrastructures bring many benefits, such as the on-demand elasticity for resource usage, a better cost efficiency, and an independent scalability for resources. There has already been a series of products. For example, the Liquid Smart Stack, which creates a GPU pool and dynamically configure the allocation to hosts. Also, Grok Rack and Infabrica ACFS, which creates extensible accelerator network. Also, the GigaO Fabric X, which I will cover later in this work. The composable infrastructures are made possible thanks to interconnect technology such as Routable PCIe. As we know, PCIe is the de facto bus technology for onboard host device communication. The Routable PCIe further enables PCIe transactions to traverse across another host in a different PCIe domain. The key technology behind this PCIe networking is the non-transparent bridge. Non-transparent bridge primarily implements the address mapping between two PCIe domains. An NTB-enabled device encloses an address mapping table. For example, if a host wants to send a PCIe transaction to an endpoint in another PCIe domain, it will first visit the host adapter connected with the NTB using a local address. Then, the NTB will translate this local address into another address in other PCIe domain. Finally, with this converted address, the PCIe transaction can reach the remote endpoints. Therefore, the NTB enables a host to launch PCIe transactions to remote devices. Given that Routable PCIe has become an important underlying interconnect for composable infrastructures, it's important for us to understand its limitations and capabilities. However, we are lacking a systematic understanding of it. There are many questions unanswered. For example, as the Routable PCIe introduced extra hops, what are the latency and bandwidth overheads? How does inter-host link behave and orchestrate co-located flows? Also, how does existing PCIe interact with the new inter-host paths? To answer these questions, we present our work, rPCIeBench, to help us conduct a characterization study. The design principles of rPCIeBench include: first, generality. It should be device independent and support any Routable PCIe systems. Second, end-to-end operation. It should capture the communication performance of an entire PCIe transaction. Third, reconfigurability. It should be able to launch different patterns of traffic as desired by users. The rPCIeBench is a hardware and software co-designed benchmarking network. The hardware parts include a host server, an external Routable PCIe switch, and a standalone chassis where accelerators are placed. The software on the host side include the application, runtime library, and device driver. The application provides a performance profiler to capture the performance of a PCIe transaction, and also provide APIs for users to invoke the communication. The runtime library has a memory manager and a pooling-based notification system for completion. The device drivers allows to issue memory-mapped I/O and direct memory access. The software part on the accelerator side include custom logics, which handles the command execution of communication, and the PCIe subsystem to support MMIO and DMA. They are in the FPGA B stream. The key enabler of rPCIeBench is the communication primitives we implement to capture different data movement directions. We mainly implement 4 DMA-based primitives. The first is a host-to-device. The host will first issue a command to a remote device, which invokes a DMA read to copy data from host memory to the device. After the DMA finishes, the device will post the completion word to the host. The second is a device-to-host. The host will still issue the command first, and then a DMA write will be invoked to copy data from device to host memory. And finally, a completion word is posted by the device. The third one is device-to-device read. After the host issues a command, a DMA read will be invoked to copy data from another device. After the data is received, the device will post completion word. The last one is a device-to-device write. After a host issues the command, a DMA write will be invoked to copy data to another device. Now, it's the device who receives the data that posts the completion word back. Now, let's look at the characterization of a Routable PCIe. But before we dive into details, let me discuss about our experiment setup. The hardware we use is a Dell PowerEdge R740 platform with an Intel Xeon Gold 6248 CPU. We use PCIe Gen 3 by 16 links. The Routable PCIe switch we choose is GigaIO Fabric X RS4024. And the standalone chassis we use is GigaIO RB4882R2. We pick up Silic's Elvo U55C FPGA as the accelerators. For the software, our operating system is Ubuntu 2004 with the Linux kernel version 5.3. The FPGA development toolchain we use is Xilinx Vivado 2022 with Chisel 3.44. We conduct a systematic characterization on the Routable PCIe performance. Our characterization results can be divided into two parts. The first part is the basic performance of a single Routable PCIe path. We mainly focus the latency and bandwidth overhead, latency versus throughput property, bandwidth partitioning, tail latency, and communication asymmetry. The second part is the performance of multiple flows on a shared Routable PCIe fabric. We look at the bandwidth allocation, the bandwidth synchronization, and orthogonal paths. In this presentation, I will mainly focus on the first 3 items in part 1 and the first 2 items in part 2. First, let's look at the one-way latency of Routable PCIe. The one-way latency is the one-way PCIe transfer from the host root complex to a local or Routable PCIe endpoint. We launch MMIO from the host root complex to the endpoint. The y-axis is the one-way latency we measured. From this figure, we can see the Routable PCIe incurs a 489.6 nanosecond one-way latency overhead. We further work with the device vendor to perform an end-to-end latency breakdown. The NTB switching chips at host adapter, external PCIe switch, and endpoint adapter each add a 105 nanosecond latency. Two copper wire each has a 5 nanosecond propagation delay. The external PCIe switch has a processing delay of 10 nanoseconds, and the rest 150 nanoseconds is due to host-side software. From this, we learned that the Routable PCIe is not as performant as local PCIe due to the extra hops. Next, we will look at the bandwidth overhead. We launch PCIe transactions to fully utilize the bandwidth of PCIe paths, and we launch in both host-to-device direction and host-to-device direction. The y-axis shows the bandwidth of local and Routable bandwidth we measured. We find there is a 30.4% and 6.9% bandwidth degradation for host-to-device and device-to-host communication. What we learn is that the Routable PCIe hurts bandwidth due to a lower transaction rates of the external switch. Next, we will look at the local versus Routable. We will look at latency throughput property of local PCIe and Routable PCIe. We launch multiple flows to utilize the bandwidth of PCIe paths and send probe flows into the paths with their latency measured. The x-axis shows the bandwidth of the PCIe path, and the y-axis is the latency of probe flows. We find that the Routable PCIe increases latency more when the credit starvation occurs. We learned that the Routable PCIe takes more time to replenish credits. After we look at the basic performance of a single Routable PCIe path, now we will examine the performance of multiple flows on a shared Routable PCIe fabric. To conduct this in-fabric traffic orchestration analysis, we create 3 scenarios with multiple flows contending on, first, the host adapter, second, the endpoint adapter, and third, the external switch. We launch 2 flows contending on a common link and check their bandwidth share. We use different PCIe request size to create different bandwidth demands. We set the PCIe request size of flow 1 to a fixed number, and we vary the PCIe request size of flow 2. As the PCIe request size of flow 2 increases, we then check the bandwidth share of these two flows. As we can see from the left figure, if the link bandwidth is undersubscribed, each of the co-located flow gets its desired rate, and the flow 1's bandwidth is not affected by the other flow. However, if the link bandwidth is oversubscribed, as we can see, as the PCIe bandwidth demand of flow 2 increases, the flow 1 has to yield its bandwidth to the flow 2. That means now, if the bandwidth is oversubscribed, each co-located flow gets a max-min share. Finally, these two flows reach both the 6 GB per second bandwidth, which is half of the link capacity. We learned from this that the Routable PCIe fabric applies a credit round-robin scheduling, which follows the basic scheme of PCIe. Next, we will look at the bandwidth synchronization. We send out multiple flows in the path to utilize the bandwidth, and then we send out one packet probe flows with their latency measured. From this figure, we can see the tail latency of those probe flows varies little when increasing the bandwidth utilization. The thing we learn here is that the bandwidth availability can be quickly backpropagated along the path because there is little queuing effects in Routable PCIe fabric. After we examine the characterization of Routable PCIe performance, we now further go towards the bandwidth estimation on Routable PCIe. Our goal is to estimate the bandwidth allocation with multiple flows sharing a common Routable PCIe fabric. To achieve this goal, we propose an algorithm called age constraint relaxing, which takes the fabric topology and the flow profile, including direction and bandwidth demand as the inputs. And then the algorithm will output the estimated per flow bandwidth. The key insights behind this is that we encode our characterization insights into 4 traffic orchestration rules. The first rule is the maximum bandwidth bound of a single link. That is, the aggregated bandwidth should never exceed the link capacity, which is characterization part 1.2. The second rule is the bandwidth partition of a single link. That describes the bandwidth share of multiple flows sharing exactly the same source and destination, which is characterization part 1.4. The third rule is the approximate max-min fair bandwidth allocation. When multiple flows are sharing a common link, their bandwidth share should be a max-min fairness, which is the characterization part 2.1 we just discussed. The last one is an isolated communication domains. That is, the orthogonal paths have no effects on each other, which is the characterization part 2.3. For more details of these 4 rules, you can find in our paper. Now let's discuss this age constraints relaxing algorithm. The key idea is to iteratively use age-induced constraints to update the bandwidth estimation. We use our testbed topology as an example. At the beginning of the iteration, we set the bandwidth demand as the bandwidth estimation. And then we check each flow to find which of these, we check each age to find which of these ages are oversubscribed. For example, now the age HS is oversubscribed. It breaks the rule 1 because it has flow 1 and flow 3. The aggregated of these two flows is 15 GB per second, which is larger than its capacity, 12 GB per second. Then we apply the rule 3 to find the max-min share of the capacity, which should be 6 and 6 GB per second. That enforces two constraints on the flow 1 and 3. After we find all the ages and all the constraints, we now update the flow bandwidth estimation of the flows. We always use the largest constraints as the next bandwidth estimation. After one iteration, we will use the last bandwidth estimation as the next iteration input. And then we continue this procedure until we reach a point that now all the ages are undersubscribed, which means all of the ages follow rule 1. And now the bandwidth estimation is the final output. We further conduct a validation experiment to prove its correctness. This figure shows the estimated bandwidth and the actually measured bandwidth for multiple flows sharing the common fabric of our testbed. We find that these two bandwidths are very close to each other. The validation experiment has an average error rate of 2.9%. To sum up, Composable inference structures have become important on the laying interconnect. Routable PCIe has become important on the laying interconnect for composable inference structures. So it's important for us to know its limitations and capacities. To do this, we present our rPCIeBench, which is a software-hardware co-design benchmarking framework. The software of rPCIeBench includes APIs, runtime library, device driver, and accelerator bitstream. The hardware includes the host servers, Routable PCIe fabric, and the accelerators. We perform a systematic characterization of the Routable PCIe performance using the GigaIO Fabric X and our rPCIeBench. We report the basic performance of a single Routable PCIe and the performance of multiple flows sharing a common Routable PCIe fabric. Finally, we propose an age-constraint relaxing algorithm for the bandwidth estimation. Our tool, the source code of our tool can be found in these websites. Thanks for listening. I'm happy to take questions.